this is actually called the famous Rosenbrock function. But Rosenbrock function is something n-dimensional. So I kind of, put by a very simplified version in 2 dimension. Okay, I mean we can memorize this fact. So in general, it looks like this. Okay, so in general, it should look like this. So in general. So in general, Rosenbrock function look like this. It's an n dimension. So this is a coefficient, it's b. And how big this b is, or say how big the ratio of b versus this number is. So let me still write down the 2 dimension. Okay, so n dimension. Yeah, let me write down the n dimension. So the n dimension looks like this. So it's a summation of this k, okay, from 1 up to n minus 1, and it is xk plus 1, subtract xk square, there we have a square as well, plus, so a subtract x1 square. So this is a famous Rosenbrock function, and so everything is squared, right? So we have this term square, and it's been multiplied with a positive number. So in general, okay, so we choose A and B. So A doesn't have to be positive, but normally it's A just be chosen as 1. Simplistic. And
is it n minus 1, the summation? A summation of?
Yes, it sums to, so in general, in Rn, okay, so x is x1 to x sub n. Okay. So as we can see, when k is n minus 1, this is x sub n minus 1, and this is our last component. Okay? So this function has, so f, this function has a unique, actually a unique local minimizer. All right. And it is x star equals A. So all A's. And all right. So which tells us in the 2 dimension, okay. Oh, by the way, let me write down the name of it. So this is called Rosenbrock function. And this is a very famous benchmark problem in optimization. So it actually, it was invented many years ago, but it has been repopularized by the machine learning algorithm because it has this trait of a machine learning loss function that it has a very, very flat, like plateau, that once, I don't know, our optimizer hits this plateau, it's very hard to move toward this local minimizer. Okay, so in a sense, it's kind of very similar to machine learning loss function that we normally see our optimization process stalled, for a long, long time, and we don't know where to go. So, all right, so let's verify it. So now let's take the derivative. Okay, so gradient. So the gradient is partial f, partial x1, partial f, partial x2. in general. Okay. So we'll focus here. So we use chain rule. What we have is, so the first term we take derivative, we use chain rule, we get 200 x2 subtract x1 squared times, okay, minus 2x1. And then we have the second term. If we take derivative of that, we use chain rule. It's 2 times 1 minus x1. Then we times minus 1. Okay. So same thing. For x2, we only have the first term, so it's going to be 200 x2 subtract x1 squared. And then if we use chain rule, it's multiplied by 1. All right. So now, so let's instead of taking the Hessian, let's look at part B first. So part B asks us to find the first order necessary condition. So first order necessary condition says the following. So at the local minimum, or for this local minimizer, if we evaluate the gradient, its dot product with every feasible direction. Okay. All right. So there's a simple corollary of the first order necessary condition, and it is, think about this. So if at a point, okay, so originally we consider our optimization domain this omega, okay. So if we're at a boundary point, so this D is not a feasible direction because it goes outside, okay. So when we consider a point, whoops, this is bad. So if we want to check this x, whether this x satisfies the first order necessary condition. So if we're at a boundary point, okay, not all directions are feasible direction, but if we're at an interior point, okay, so if we're at here, then every possible direction is a feasible direction, because if our step is small enough, we won't go outside. So this is literally the definition of an interior point. That is, if our step is small enough, we won't go outside. It's also the definition of open step, but I don't want to go too rigorous here, you know. But okay, so now back to this problem is, because it considers the minimization. So if the minimization problem is for the full domain, okay. All right. And given, so, and remember when we prove the first order necessary condition, we have to use Taylor expansion up to the second derivative, which means we have to use Hessian. So here, what happens is we have to assume, okay, so f is twicely differentiable. Okay, so f is twice differentiable. Okay. If we're looking for this problem and f is twice differentiable, then the first order necessary for f's local minimizer, okay, first order necessary condition for this f is actually, this has to be exactly 0. I mean, to think why, this is pretty straightforward to verify, because if this is true, all right, then this feasible direction D, feasible direction D is all R2. In general, it's all Rn. Okay. So feasible direction D is, in this case, it's R2, and we make it a unit vector so that it represents a direction. So then what happens is this inner product or dot product with every feasible direction, it has to be greater than 0. Think about this. So we have one feasible direction, okay? So if it's positive, now we choose, for example, so we choose D1. So let's say if X star satisfies the first order necessary condition, okay, then this implies, okay, this implies what? This implies its inner product with D1 is greater than or equal to 0, okay? But then, by this inequality, this implies, if we negate this D1, if we multiply with minus D1, this has to be less than or equal to 0. I mean, by this inequality to this inequality, okay? However, this is a feasible direction as well, okay? This is a feasible direction as well, minus D1. If minus D1 is not a feasible direction, we're kind of, in that case. So, but it is feasible, which means if it's feasible direction, it satisfies the first order necessary condition. It means this has to be positive again, okay? So which one is correct? Both of them are correct, okay? So the only possibility is they are 0. I mean, this is 0, so this implies so dot D1 is 0, and this D1 is arbitrary. And by the arbitrary of D1, because we can choose arbitrary D1. Okay. All right. So the gradient is 0. Okay. So when we do research, we may ask this question. When we do research, we may ask this question. So we proved the mathematical theorem. Okay. We may ask this question is, why we need f is twicely differentiable? Okay. So can we construct a counterexample such that f is not twicely differentiable, and then the derivative is not 0? Okay. So we have to, not we have to, but it's very good, it's very beneficial that we memorize lots of examples. Okay. So don't memorize formulas. All right. I mean, but once you memorize the examples, formulas will be memorized automatically. But if we memorize these examples, so one typical example, and we can have lots of simple examples. So this is a counterexample. Okay, so y equals absolute value of x. This point is a local minimum, right? So I mean, it's lower than its neighbors. However, this point doesn't satisfy the first order necessary condition for local minimum, because f is not twicely differentiable at this point. Okay. If we take derivative from this direction, the derivative is -1. If we take derivative from this direction, the derivative is +1. Okay. So this is a typical function, the absolute value function. So in general, L1. So we will see this a lot in machine learning. So this is called L1 regularization. So if you're a statistician, this is called Laxo. Okay. So this is a typical example that this is violated. Okay, now let's back to the problem we want to solve for a point that satisfies the okay, so the first order necessary condition. So we set the gradient f equals 0 because the minimization is taken for all x in R2, which means if a point satisfies the first order necessary condition, and this function is apparently smooth, it has no actual value whatsoever. So it has to be 0. Okay, so now let's just set this to be 0. So if we set this to be 0, so we have this is, we simplify our a little bit. So we have this is minus 200 x2 subtract x1 square. Okay. Plus, oh, it's minus. Yeah, it's plus. Okay, so it's plus x1 subtract 1 equals 0, and so 200 x square subtract x1 square equals 0. Okay. So I want to solve this. This is not a linear system. This is a nonlinear system. So for a nonlinear system, I mean, the best way to solve this is first observe it. You know. So as we say it again.
In the second portion, we can put 0.
Where is 0?
In the second portion, I mean second line.
Yeah.
So we can replace this in the first.
Yes. So we start from the second equation. That's a very good strategy. Okay.
Yeah.
So this is 0, and we couldn't help but observe this term also appears here. All right.
Yeah.
So look at this. So for the nonlinear. So for the nonlinear equation, the best strategy is to.
Where did the negative 2x1 go?
Oh, thank you very much. Yeah.
Minus 2x1.
And shouldn't that be minus 2?
Yes,
Your
you're
Oh, I moved the minus sign in front.
Oh, okay.
So the idea to solve nonlinear equation is we observe first. For example, for this one is we notice that this one is 0, but we have the same term here. So when we plug in 2 into 1, all we have is this implies this term is 0. 2 times x minus y is 0. Okay. So x equals 1. So x1 equals 1.
No.
And then we plug in this to equation number 2, we get x2 is 1 as well. So in general, this can be solved for n-dimensional problem. I mean, the strategy is the same. So what happens, even if we, for the n dimension, it will be the same. I mean, you can try it. It's, the procedure is exactly the same. Okay. I don't want to erase it. Okay, fine. So now let's take the hash. IT promised me they'll send a technician to look at it ASAP. Where is IT, by the way? Anybody knows?
It's on the fourth floor. It's on the fourth floor at the Flation Hall.
Oh.
Yeah, it's just near the computer lab.
All right. So anyway, so now let's take the Hessian. So Hessian is the first row is gradient of we take gradient of partial f partial x1. Okay. And we take gradient of partial x2. So for example, so this will be so this will be the first term will be x1 twice, and the second term will be we take partial x1 first, we take partial x2 second, and then we have this term, that is we take partial x2 first, we take partial x1 second, and the last term is we take partial x2 twice. So now let's take the derivative. For example, this is our partial x1, right? So this is our partial f partial x1. This is our partial f partial x2. Okay. So partial f partial x1 twice is partial. We take partial derivative of x1 of the first term. Okay, so we use chain rule, and maybe a few, maybe not chain rule. Maybe we just expand it. Okay, so here what we have is partial x1. So minus 200, then we'll have 400. X2. x1 plus 2x1 cubed plus 2x1 minus 2. Thanks. Yeah, I heard that class. I think it's why. It's for the screen. Is it for the screen? Oh, okay. This is one. It's not. Anyway, so. Alright, so now let's take derivative of this. So, for example, when we take partial derivative of x1, x2 is a constant number. Okay. So the first term gives us minus 400 x2 plus, so we'll have this 1200 x1 squared, then plus 2. So now let's take this term, that is, equals partial x2 of whatever is here. So we have this is minus 400 x2 x1 plus 400 x1 cubed plus 2x1 minus 2. Okay. So again, we take derivative of x2, we treat x1 as a constant. So now it becomes, the first term is minus 400 x1, and all the rest term has nothing to do with x2, so it's just this guy. Okay. Next is this. Okay. So these two are equal. All right. Because our function has no absolute value, has no any discontinuities. Okay, so this function is perfectly continuous, and so we don't have to. I mean, in the exam we can write this. I have no problem with that. You don't have to compute again. And lastly is we take partial x2 twice, so this is partial x2 of what's over there, which is 200 x2 subtract 200 x1 square. Okay. So if we take derivative of this, we'll just get 200. So I'm really amazed how engineering scientists, I think engineers, so they came up with this function many years ago. This function has all the, let's say, the traits for the difficulty of an optimization problem. For example, the coefficient in front, oops, I erased it. Okay, so let's write on the function here. Okay. So this function has all the traits of the difficulty in the optimization. If we choose this coefficient, because it doesn't matter, actually, it doesn't matter what number we choose here. The local minimizer will always be 1, 1, all right? But if we choose this number very big, the condition number will be very bad, will be very big. So now let's compute it. I think the third question is asking us, does this point satisfy second order sufficient condition? Actually, I do believe it satisfies. Okay. So, all right, second order sufficient condition says the following: in order a point is a local minimizer, okay? So if a sufficient condition is first, this is 0, and the second is this one, is positive definite, like in a small neighborhood. Of x star. Okay. So equivalent condition is this guy is positive definite at x star. Okay. Oh, sorry. I think yeah. So equivalent condition. So it's either this guy or, because they are kind of equivalent. Okay. Or the hashing is positive at x star. Because of the continuity of f, so these two conditions are somehow equivalent. So now let's verify it. So now the hashing at x star is, we just plug in what we had. Okay. So for example, we plug in x2 equals 1. So basically is what do we have computed? If we plug in x1 equals 1, x2 equals 1, and we evaluate it. we plug in first one here, it's minus 400 plus plus 1200, then plus 2. So we have 802. And the last component is already 200. And this is minus 400. Okay. So we want to take the eigenvalue, so check the eigenvalue of this. All right, so this is the first way. The second way is we directly use the second derivative test. Okay. All right, so second derivative, so this is, let's just do the Hessian check. Okay. So this way is faster. All right. So second derivative test says, okay, the diagonal is positive. Each diagonal entry is positive. So it's good. All right. So diagonal entry is positive. Because 802 subtract. Sorry. So 802 is positive. 200 is positive. So diagonal entry is positive. Then we want to check the determinant is positive. Okay. All right. So the determinant is what? Determinant is 802 times 200 subtract minus 400 square. All right. So what's happening is it's barely positive, right? I mean, so comparing with the magnitude of this, okay? So I think this is 400, is it? Okay, so it's positive, so we check. So determinant is positive, diagonal entry is positive, so which means the eigenvalue, actually this in turn implies the eigenvalue we derived and maybe in our first week that this is a second derivative test, okay? So the answer is yes, this point does satisfy, okay? So the answer to the third question is yes. Okay. So the local minimizer does satisfy the second order sufficient condition, and in our coding homework, next coding homework, we'll try our optimizer coded for this function. So now let's move on to problem B. So problem B actually is one of our homework, but think about this. Okay. So we have exactly the same homework problem in our exam, so the chance of that is kind of not very big, okay? But, for example, okay, all right, so, and also, for part B, so let me talk. So this is our objective function. This is our objective function, and it is, so we derived it in our last class that, so we simply expand it, and we'll have this as X transpose, A transpose AX, subtract 2 times, so X transpose A transpose B, okay, plus B transpose B, we derive this. All right. Okay, so this equals AX inner product with, so this equals AX inner product with AX. This 2 equals this 2 AX inner product with B, and this one is B inner product with B itself. Okay. So when we take the derivative, when we want to use our existing formula, that is the gradient of 1/2 x transpose qx subtract b transpose x is qx subtract b. Okay, so when we want to use this existing formula, we want to rewrite the second term in terms of something transpose times x transpose. Okay, so we can group this into two parts. That okay. So what happens is this is then x transpose a transpose a x subtract 2 times. Okay, so it's x transpose this guy. It's also this guy transpose times x. So it's a transpose b transpose times x. Okay, plus b transpose b. So now we can use that formula now. So now we can use the formula. The gradient of f is then 2 times a transpose ax subtract 2 times a transpose b. Okay. I mean, once we have done enough, this is actually linear regression. So if we set this to be 0, we get the normal equation for the linear regression. Okay. So now my question is, let's suppose in our exam, what if we have a regularizer term? So this is called a ridge regression. I mean, what if we have this? So ridge regression is a common way of preventing overfitting. The idea is we want our solution converge to the unit ball. So we don't want our solution diverge to a far away place, away from the origin, but instead we want our solution converge as close to the origin as possible. Okay. So how do we take derivative of this? Okay. So I mean, let's take derivative of this separately. So if we have g of x equals alpha, which alpha is a number, okay, the simplest way to take derivative is we rewrite it as x inner product with x, okay? And the simplest way is to treat x as identity times x. And we move this alpha inside. Okay. All right. So, I mean, so this is our Q, okay? Not exactly our Q, but we want a Q to be symmetric. This is symmetric though, but it has half factor, so it has one factor off. So when we take derivative of this, so when we take derivative of g, what we will get we'll have 2 alpha identity times x. Okay, so 2 times this q times x. So this is the same thing as 2 alpha x. All right. So this is just an analogy. This is an analogy of taking the gradient of square in n dimension. Okay? Think about this. This is like a square. Let's take the norm of x. I mean, okay? So sometimes we can even, for example, so in advanced ridge regression, so sometimes we can add a preconditional. So what does preconditional ridge regression mean? Is we can even add something like this. Okay. So this is our regularizer function. So this is alpha qx times x. So we make the condition number of the linear regression with ridge regularizer even better. So we add a matrix here, Q, that balance the condition number of this A transpose A. But, I mean, these will be taught in the statistics graduate class learning linear model, so it's out of scope of our class, but we need to know how to take derivative of this. Okay. For example, to take gradient of this, what do we get? So we get 2 times alpha qx. Okay. Anyway, so now let's move on to the problem B. So it says, find the largest range. Is it false? No. So it says, find the largest range find the largest range of step size values for A matrix in the gradient method that our gradient method will converge. So I mean this is not very difficult. I don't want to use alpha, so maybe the alpha step size. K, so alpha k must be in between 2 divided by lambda max of q, okay, where q is in this function. So in this case, in this problem 2, in problem 2, Q is what? Q is 2 times this guy. Q is 2 times A transpose A, which is 2 times this guy, transpose times itself. Again, diagonal matrix, the eigenvalue is just it's diagonal entry. Okay, so lambda max Q then 2 times squared. Okay. Yes.
Why are we not just using A, because A is technically already square, like
because this is our Q, this is our f of x. So this is our 2 times Q. Sorry, 1/2 Q. So this matrix here is our 1/2 Q. It's linear regression. Linear regression, the condition number doubles versus the original matrix A. All right, so now then the range is, we plug in this, we'll have, this is nothing but our step size has to be between 1 and 1 over this 12 squared, which is 1 over 144. So, I mean, leaving last step without computing. So, for example, I mean, this exam doesn't need a calculator. I mean, if you want to bring a calculator, it's totally fine. But in general, you can leave the answer like so. We have to require. Okay, to require something like this. So then, the C, okay. So it says, if B is 0, so vector 0, just 0, 0, what is x star? All right. Remember.
Is this 404?
403. Yeah. This lady doesn't even know the classroom half the semester. So. But she seems to be looking for someone though. She's not a student of our neighbor classroom. So if B is 0, okay, think about this. So our x star, okay. So our x star is the solution to this. So this is the solution. A transpose A inverse A transpose B. Okay, so if A transpose A inverse exists, okay, so its inverse matrix doesn't always exist. Okay. All right. But this one doesn't always exist. So that's a factor. All right.
So I didn't understand this part, like x star equal to, how did you write it?
Which part?
The x star A, the inverse one.
Here. So we solve. So first order necessary condition. Then we solve f equals 0. Then
Okay.
okay. For example, so here it is 2 A transpose A times x subtract 2 A transpose B is 0.
Yeah.
So we solve this linear system.
Okay.
Right? So it's this, if this exists, but in general answer, so I mean, then in our case, in our problem, okay, so in our problem, x star, A transpose A is nothing but this matrix, okay? So this matrix as the diagonal matrix is inverse, of course, it exists, but so in our problem, so in C. Okay, but in general, is x star satisfies. Okay. Okay. In general, x star satisfies A x equals 0. So part B of C is asking us apply the steepest descent method to find x1. Okay. All right. So keep in mind there's a homework problem. Okay. There's a homework problem saying, okay. So if this is, so if the difference is parallel to one of the eigendirections, so if where Vi is an eigenvector of Q, what is Q? Q is the Q in 1/2 x transpose Q subtract Bx, okay? So then, so we derived, what happens is, then if we apply the steepest descent one time, we will reach the local minimum. So we search on this line so that so in the exam we can either quote, okay, so we can either quote this or we just plug in the steepest descent formula that we try to solve a minimization problem by line search. Okay. So for example, if we apply line search, let's see what happens. So for example, so actually the formula of steepest descent is given on the first page. Think about it. So on the formula page, the CG's formula, conjugate gradient formula, will be given, but the first iteration of conjugate gradient is steepest descent. Okay, so it's like if we know that, then we just plug in the formula. So let's try it, and so gradient of f is 2 times A transpose AX subtract 2 times A transpose B. Okay. So this is our gradient of f. All right. And so our gradient of f evaluated at x0 is 1, 0. Okay. B is 0, so it's 2 times A transpose, okay, times 1, 0. So it's going to be 2 times 12 squared. And then the step size, so the step size by the formula we had in on the first page. So let's do alpha 0. Okay. So it is G inner product with G0 inner product with G0 divided by Q G0 inner product with G0. Okay. I mean G0 is this gradient. Okay. Sorry. What am I doing? My bad. This is a vector. So it's going to be, the first row is going to be 2 times, it's going to be this, my bad, sorry. Okay. So now let's compute it. Let's compute this. Okay. So the top is this guy inner product with itself. What we will have is 4 times 12 to the 4th power. Okay. On the bottom, what we will have is 2 times 12 square 0 times this diagonal matrix. Q is 2 times that. Okay. Q is 2 times AA transpose, so it's 2 times 12 square, 5 square, 0, 0 on the off diagonal times 2 times 12 square 0. Okay. Okay. So we have this formula, I mean, from linear algebra. Okay. So we have this formula that if we have a block, so let me don't use A, let me use block 1, block 2, 1, 1, 2, 2, 1, 2, 2, 1, okay? And then we have this vector, for example, we have this U1, so U1 has the same dimension with B11 and U10, okay? So when we have this, this is X transpose times Q times X. So what happens is only B1 block will be multiplied. So think about this. So this is U10. When we multiply this side, we'll get B11 U1, and this is B21 times U1. But then when this guy multiply with this guy, okay, what happens is so this multiply with this, the second will be 0. So we're left with U1 transpose multiply with this. So it's going to be U1 transpose. This should be U1 transpose, U1 transpose, B11, U1. So same thing here. So, I mean, when this is 0, so only the first term got counted. So we will have this is 4 times 12 to the 4th power, and then we'll have 2 times 12 square, and times this guy here, times 2 times 12 square, okay, times, and we have 2 times 12 square, so this cancels with 2 copies of 2 times 12 square downstairs, and add the denominator, and so we have this. Okay, so this is our step size, and then we move in the direction of negative gradient. So x1 is x0 subtract alpha 0 gradient evaluated at x equals 0. Okay, that's a gradient. This is a gradient. This is the step size. Okay, so perfectly balanced. So we have this is 1, 0 subtract. This is the step size is 1 over 2 times 12 square, and the gradient is 2 times 12 square 0. Okay, so this is 0, 0. So we reach the minimum in 1 iteration. So that's this is like a so by the theorem. So when we try to solve the midterm, before we write down the solution, we should have an expectation of what the correct answer is, and then we move toward that direction. Okay, so the problem we were given in a very similar fashion is the actual midterm. For example, this one, you know, and especially so for the third problem. Okay, so so for example, it's application of CG. Okay, all right. So again, this one is one of the homework problem, but apparently we won't be we won't be having the exact same problem. So I mean, here, right? So for example, so f, let's write down f in the expression of this. Okay, so f is 1/2 x transpose. So x transpose is x1, x2, but as a row vector. Okay, so then this one will be. So we first fill in the diagonal. The diagonal will be the coefficient. For example, this will be the coefficient of x1 square. Let me just mark the marker. Okay. So this will be the coefficient of x1 square. Okay, this will be the coefficient of x2 square. But because we have a 1/2 in front, we just, so this is the coefficient of x2 square. Just we take care of the 1/2 in front, then we can fill in the blanks. Okay. So for example, then the off diagonal, because we want a symmetry, so we just fill in what's happening. So if we have 2 there, okay, then we just fill in this 2 too. Okay. It's this. And then so subtract x1 is 3, 1 times x. Okay, so x is x1, x2. Right. Okay. So let's make sure Q is SPD again. So this is our Q, right? So Q is 5, 2, 2, 1. Okay. So we can apply, apply the second derivative test. So its diagonal entries are greater than 0. Right? 5, 1. Diagonal entry bigger than 0. Determinant. So 5 is greater than 0. 1 is greater than 0. And if we don't like to solve the eigenvalue, we just argue the determinant of the Q. So diagonal entry greater than 0. Determinant of Q is greater than 0. Good. Okay. Determinant of Q is 5 subtract 4, which is 1. Okay. Then these two implies. So this only applies for 2 by 2 matrix. Okay. So this implies Q is positive. So now if we look at the second problem, that is find the minimizer of f using conjugate gradient algorithm by hand using the initial guess x0 equals 0, 0. So I won't perform it here, but the expectation is, okay. So remember, conjugate gradient is we search the minimizer in a subspace, okay. So when we enlarge this subspace to dimension 2 in the second iteration, it's like we solved the global minimizer problem. So CG, okay, should converge to, okay, x star in 2 iterations at most. Okay. When the dimension is 2. Okay. So in our exam, if the numbers, so this is like a guarantee, if when we plug in CG, so we're getting far away. So for example, for this problem, the minimizer is, so x star should satisfy qx star equals b. Okay. All right, so we solved this. We had a sense of where our local minimizer is. So if our CG, so if when plug in by hand, we get far and far away from the point we should get, then we're doing something wrong. Okay. So that's it for today. So for the coding question, you guys can plug in the code to our Google Colab to see the output. Okay. But it won't be that many, but we will maybe have 1 or 2 coding questions. And then we'll have like the 3 problems in a very similar format with practice. Okay.
Thank you.
So the midterm is next class, right? The midterm is next class. Thursday.
Are you sure?
Yeah, he said it.
It's on their front.
Yeah.
One more time. No, he said if it's
You can check that. Do you know how to solve 3 by 3?
Yeah.
You didn't solve the 3 by 3. You didn't? You sure? It's not even 3 by 3? How do you do this, for example? Making things up.
Appreciate it.
Do you know how to solve analytically?
Thank you.
You don't know? You sure? You learn linear algebra. You sure? You learn linear algebra. You learn linear algebra, yes or no? You haven't learned linear algebra.
Like what it was in general.
Have you taken
Yeah,
any
I
linear
did.
algebra class? Yes or no?
You can just take a picture and the purple is probably what,
Without knowing the linear algebra. Wow, that's really it.
I don't know. It was like what he, just like what it means.
Okay.
And then the black is like actually solving it.
Gotcha. I appreciate that.
You must have linear algebra in other videos. In other videos, you have must linear algebra.
Yeah, you had to. Almost.
Do you know how to take determinant of this?
Is this for
Yes,
the-
yes.
Do you know how to take 3 by 3 determinant?
Yeah,
You know?
yeah.
It's okay. I won't give you a problem.
No, I have done I know how to do it.
Okay, so if you want to find the eigenvalue of a matrix, okay, of the 3 by 3, we can do it by hand by. So if this is A, we solve this problem. Okay.
I know.
Okay, good. Then we solve for lambda, and then we solve for eigenvalue. But it takes time, you know.
I was blank out.
Okay. So, but if you learn some advanced linear algebra, which I'll teach next semester. So if your matrix is in block form, okay, is in this form. This form is nice, you know. Okay. It can be even star here. Okay. So what happens is the eigenvalue of this block matrix is the eigenvalue of A and eigenvalue of B. Okay. Star means whatever.
Whatever statement.
Whatever, because if you take determinant,
It's
okay,
upper triangular matrix.
it's not upper triangular exactly. It can look like this, you know. It can look like this. This is 0, and whatever, you know.
Okay.
So, but yeah, but this is not in the scope of this class, but we can play with this. I mean, this is for example, this is the training of a generative adversarial network, which is called GAN. That is You know, so for example, if you take determinant of this, you still do this, right? So this stuff doesn't matter, so it's actually equals determinant of A times determinant of B. So if you do lambda identity, this is lambda identity, this is lambda identity, that's why I'm saying the block matrix have the same eigenvalue with, you know, it's smaller block. But so but I mean, I want to give this type of problem, but I know many of us haven't learned these advanced techniques in linear algebra. So I don't want to torture you. So that's why I'm telling you the problem will be almost similar. You know, just adding a few different functions. Yeah.
In this problem, you can use analytic linear solve except for
Oh yeah, yes, exactly.